Okay. All right, so today we are going to be covering threshold voltages in MOSFETs. All right, so in covering threshold voltages, what we're going to talk about today in class is how, we're going to review some of the physics of what happens in strong inversion, because the threshold voltage is based on strong inversion. And then we are going to, I'm going to give you an equation for the threshold voltage, and we're going to talk about the physical concepts that drive each of the components of the threshold voltage equation. Okay. So the threshold voltage is obviously a very important part of the field effect transistor. In effect, that is when the device is considered to be on. Okay, so we're just going to build up some of those concepts from the ground up. We're going to end class today. Hopefully, we should have enough time. We'll do an example problem of calculating threshold voltages, and I think that will help you on the homeworks and just understanding some of the physical concepts. It'll bring it to life, I think. Okay. So I'm not going to go over the details of everything we've done on MOSFETs thus far. What I'm going to do is come back to a couple of the diagrams that have to do with threshold. All right, so there's two types of MOSFET devices, as we've seen. These NMOS and PMOS devices have three terminals, a gate, drain, and a source. Okay, and the way you typically operate the device is by applying a gate voltage, VGS, and then you apply a drain voltage, VDS, and then you measure the drain current, ID. Okay, but let me back up here for a second, and I just want you to remind yourselves that at the very simplistic level, okay, the MOSFET is a switch. It's an electronic switch. Okay, current flows from drain to source in an NMOS device. This is where current flow is. Okay, the gate is being used to turn the switch on or off. Okay, in the typical enhancement mode NMOS device, if the gate is a high voltage, then the switch will be on. You'll get current flow going through this way. Okay, and if the gate is not at a sufficiently high voltage, then there'll be a blockage in the current, and there will be nothing that flows from the drain to the source. All right, now, so where the threshold voltage comes in is that voltage, when we're saying it has to be greater than a certain voltage for current to flow, that is the threshold voltage. Okay, and so again, once we apply a gate voltage that's greater than the threshold, exceeding the threshold voltage, then the transistor turns on. And at that point, we can get current to flow between the drain and the source by applying a drain to source voltage. Okay. All right, and the PMOS device works in a similar manner, except your source and gate are at different places. You actually apply a positive source to gate voltage, and your current flows from source to drain instead of drain to source. Okay, so the first concept that we covered in terms of threshold voltages is this one. So really quickly. So we covered the concept of electronic switching. We covered the concept of inversion. Okay, under normal conditions and cutoff conditions, you have the source here, the drain here. These are both N-type. This is an NMOS device as an example that we're giving right now. And the gate region, under the gate region is called the channel region. And that channel region is a P-type substrate. This is the top view that we're looking at. And this is what the device looks like. There's no current that can flow between the source and the drain because you basically have two back-to-back diodes, and a PN junction here, oriented in opposite directions. So in order to turn the transistor on, you have to change this from a P-type material to an N-type material. Okay. And then at that point, you don't have these PN junctions anymore. You just have three resistors like this, and current can flow. So in the context of threshold voltage, which we're going to be talking about today, the threshold voltage is the gate voltage required to invert this channel region from a P-type to an N-type. So now we can go into one additional level of detail, is when does that happen? And we come to this slide here. Well, you know what? Let's just touch on this one again. So this was, Okay, so sorry about this. This is the inversion energy band diagram. This is what it looks like. Remember, you apply a gate to source voltage. You perform the band bending. And in this portion, just underneath the channel, you effectively inverted the semiconductor from P-type to N-type. How do we know that? Because the intrinsic level is now below the Fermi level. Okay, so out here, it's a P-type substrate. Intrinsic level is above the Fermi level. In here, the intrinsic level is below the Fermi level. Okay, we've switched it from P-type to N-type. Okay, when that happens, the electrons that are, the small amount of electrons that exist in the conduction band, they form a narrow channel in this region. Okay, another level of like threshold voltage. In order, we define threshold voltage as the voltage at which we achieve strong inversion. Okay, strong inversion is defined as a certain amount of bending in the band diagram very close to the channel. Okay, this is the oxide region, and this is the semiconductor region. Okay, remember, this is the vertical cross section that we're looking at. The metal is here, the oxide is here, the semiconductor is here. So the amount of bending that we have, which is called phi s, okay, phi s is the surface potential, that's what S stands for. Don't mix this up with the semiconductor work function. Okay, and they're both labeled phi s, unfortunately. So this describes how much bending you need to have. And the amount of bending you have to have is equal to 2 phi f. The phi f is the distance between EI and EF in the substrate region. So this is just determined by the substrate doping. And then 2 times this is the amount of bending that you need to have in the diagram. Why do we choose 2 phi f? Is because strong inversion, the way it's defined, is that the surface region is going to be a mirror image of the substrate region. So let's say this is P-type with a whole concentration of 10 to the 18th per centimeter cubed. Okay, imagine a P-type substrate with a doping density 10 to the 18th per centimeter cubed. Whole concentration is also 10 to the 18th per centimeter cubed. At the interface, the material will have become N-type with an electron concentration of 10 to the 18th per centimeter cubed. Okay, so that's how we're defining a strong inversion. Okay, the final thing we went over last time, which has relevance to the discussion on threshold voltage, is this diagram here. Okay, this is really important. I'm going to go through it quickly. If you need to know the details, go back to the previous lecture. You have the metal, the oxide, and the semiconductor. You apply a gate voltage. You build up positive charge on the metal, and then there is an electric field that goes through the oxide and the insulator. That does 2 things. It creates a depletion region by pushing away the mobile holes in the substrate. And then it also creates an inversion region by pulling in the minority electrons. So this is QD, this is Q sub S. And in class last time, we talked about all the different equations that describe this phenomena. And we're going to be bringing some of these concepts in again. Okay, but some of the key concepts here is that you have a buildup of positive charge here, high positive charge concentration. This is mobile charge. A high negative charge concentration here. These are mobile electrons. This is the surface charge. These electrons are also mobile. This is what creates the conductive channel between the drain and the source. The source is over here, the drain is over here, so these electrons can flow back and forth just in this region. The depletion region is also negatively charged, but these are immobile ions. These are immobile ions. Okay, so one concept that is going to be related to the threshold voltages is this concept of charge equality. The amount of negative charge that we have at the bottom, so QD and QS, that's the total negative charge here, has to be equal to the amount of positive charge that we have up here on the gate. Okay, and the amount of positive charge that we have up here on the gate, it is related to how much voltage we apply. Okay, so this is all related. So for example, we're going to be talking about the body effect or substrate doping. If you have a substrate doping that increases QD and you end up having more negative charge, that means you're going to have more positive charge in the metal. in order to create an inversion channel, and therefore you're going to need a larger threshold voltage, a larger voltage to achieve strong inversion. Your threshold voltage is going to be larger. So that's going to be one of the things we talk about today. The substrate doping has an impact on the threshold voltage. Okay, so last thing we talked about in class, and this is going to be very important in the discussion of the threshold voltage, is this the electrostatics. Okay, so we basically said there's a bunch of metal, a bunch of positive charge in the metal. This is going from the metal to the oxide to the semiconductor, going in the horizontal direction. It's a bunch of charge here. There's a bunch of negative charge in the inversion channel. There's some amount of negative charge in the depletion region. And this positive charge, this area under here, is equal to this area here. Okay. If you integrate the charge, you can find the electric field. And so the strongest electric field is through the oxide. The electric field dropped down suddenly over this surface region, and then it drops down more slowly across the depletion region. Corresponding to that electric field, there's voltage drops, okay? And a very important concept in electronics is that everywhere where you have electric fields, there is a corresponding voltage drop, okay? And you can find that voltage drop by integrating the electric field, okay? So we have an electric field here. That means there has to be a voltage drop. The electric field exists in the oxide. That's where the electric field is strongest. So there's going to be a voltage drop across the oxide. So if we go back to this diagram, imagine that we apply a VGS, okay? Some of that VGS is going to be dropped over the oxide, and the rest of it is going to be dropped over the channel. Okay, for those of you who aren't electrical engineers, what does a voltage drop mean? This VGS that you see here, that means the voltage up here in this node is VGS. The voltage here is 0. You can see it's connected to ground. So through this thickness here, the voltage is going to, change gradually from the VGS down to 0. So there's going to be some of that changes occurring through the oxide, and the remainder of that is occurring through what's called the surface potential. Okay, there's 2 voltage drops there. And that is what is shown here. Okay, you apply a VGS here. Okay, this is voltage versus the vertical distance here. So we're going through this direction. Okay, so this is the coordinate X. There's some voltage drop across the gate oxide. So this region is the gate oxide. And there's also some voltage drop across the semiconductor. The voltage drop across the semiconductor, to tie the concepts together, this is your phi sub s. This is the surface potential. This tells you how much band bending you have in the diagram. Okay, just to be totally clear, this phi s that you see in the diagram here, the bending in the band diagram, is the same as this phi s that you see here in this graph of the potential drop. Okay, and the sum of phi s and vi equals the gate voltage that's being applied. Okay, so now getting to the threshold voltage. In order to create a channel, to create that conductive channel, we have to be in strong inversion, as we said. So we're defining a gate voltage that's required for strong inversion, and that's called the threshold voltage. Below the threshold voltage, we kind of informally say that the transistor is off. Although if I were, there's a more advanced concept called subthreshold effects. That even below the threshold voltage, you can actually get some current flow. But that's not the topic of today's class. Today, we're going to be talking about the vanilla threshold voltage, and we kind of think about it, the devices being off below the threshold voltage and on above the threshold voltage. So the equation for threshold voltage is shown below. So I'm just showing you the equation first, and then I'm going to show you where the different aspects of that equation comes from. So the threshold voltage V sub t is equal to the flat band voltage VFB minus QD over CI. This is the depletion charge divided by the oxide capacitance. And then the third term is the amount of bending in the band diagram, the 2 phi F, the one that we showed earlier, the amount of bending in the band diagram. And those are the three parts of the threshold voltage equation. Now, what you can kind of think of is that, well, I'll get into the details of it in just a second here. So we're going to go through each one of these terms, and starting with number 1, the strong inversion term, the depletion charge term, the second one, we'll cover that second, and then we'll cover the flat band voltage, which has multiple components to it, and we'll cover that last. Okay, any questions so far? Okay. Okay, good. So let me close this. Okay. So there's 3 terms we have to think about. Let's start with the strong inversion term, since it's the same as what we discussed earlier. We have to get a certain amount of bending in the band diagram. And this phi sub s term represents that. It's equal to 2 times phi f. Okay. Just as a reminder of why we need this term, we want this section just underneath at the oxide semiconductor interface. We want this to be n-type, so that the Fermi level has to be above EI. The Fermi level is above EI, that means we are going to get electrons trapped in this potential well here. Okay, and this is the conductive channel. So remember with band diagrams is that the amount of bending that you would have is related to how much voltage that you apply. You know, if we go back to our example here, okay. Okay, just belaboring this concept again, the Fermi level, this is this on the metal side, there's a certain Fermi level. On the semiconductor, there's another Fermi level. The difference between these Fermi levels is the gate voltage that's being applied. Okay, so so in order to get more bending, we'd have to apply more potential. Okay, so we have to apply sufficient voltage so that the Fermi level on the semiconductor side is high enough so that you get a certain amount of bending in the semiconductor. Okay, moving on. So that's the first term. Okay, pretty easy to calculate. Remember that phi f is equal to kT over q ln of Na over Ni. So you can see that this term is determined by the substrate doping. Okay, the higher you dope the substrate, there's going to be, the higher your phi f is going to be. But remember, this is a logarithmic term. Okay, so the phi f is logarithmically related to the substrate concentration. All right, next. That's the first component. Now, the second component is the depletion charge here. Okay, this term, go over this here. We've already seen this diagram. Remember that there's positive charge in the metal, electric field through the oxide, depletion charge here, and then the surface charge here. This charge contributes an electric field, and so there's going to be a voltage drop across it. Okay, now one of the fundamental equations for a capacitor is Q equals CV. And if we rearrange that, V is equal to Q over C. So what that means is that if you have a capacitor, like this, this equation just tells you the relationship between voltage and charge. Okay, and this Q over C can be, let's just write down capacitance for a parallel plate type device is epsilon A over D. Remember, that's a basic capacitor. Now, how does it apply to this situation? Well, this tells you the voltage drop across a capacitor. If we know the amount of charge, Q, and we know what the capacitance is, well, we can figure out the voltage drop. As I said before, the way we're analyzing this is we have a VGS. We assume that there's some voltage drop across the oxide, some voltage drop across the depletion region, and that's how we figure out our VGS. So the voltage drop across the depletion region here, the depletion capacitance, is equal to Q over C, right? Specifically, it's the depletion charge, Q sub D, divided by Ci, where Ci is the insulator capacitance. Oops. So I gave you an equation for C. Ci is a unit capacitance. So this is just epsilon over D. It takes out the area term because the units for Ci is farads per centimeter squared. Okay, it's a unit capacitance. So I'll just put here, this is a unit capacitance. So the units is farads per centimeter squared. Capacitance per unit area. All right, so the insulator capacitance is calculated using the gate area and the thickness of the oxide. So the depletion, the voltage drop over the depletion region is QD over Ci. The depletion charge, which is this stuff here, divided by Ci. And Ci is epsilon over D. Units for Ci is farads per centimeter squared. Okay, any questions on this? Okay. Next part. This is the voltage drop due to the flat band voltage. Okay, so this involves some different aspects here. Okay, so we have to think about this for a little bit. So in the previous example that we did, if I can pull that back up, the metal and semiconductor work functions were the same. And I mentioned that in class that, hey, we're just doing this for the time being because we want the concept to be simple at this point. And later, we're going to introduce the concept of having phi m and phi s not be equal to each other. Okay, so again, let's come back to the equilibrium band diagram here. When we drew the equilibrium band diagram, we started off with the metal and the semiconductor being at equal Fermi levels because no voltage is being applied between the gate and the source. Remember, this is equilibrium. All right, and we drew the band diagram for the metal, we drew the band for the oxide, and then we drew it for the semiconductor as well. All right, the key point I want to make here is you see how phi m and phi s are equal to each other here? They just happen to be equal in this diagram. And as a result of that, there's no bending. EO is here in the semiconductor. It's just a flat line across, just like the Fermi levels are. Okay, this would only happen if phi m and phi s are equal to each other, right? Let me throw out a question then. What do you think would happen if phi s were much larger than phi m? So give it a thought. Imagine this diagram where phi s was much larger than phi m.
We do have bending where it's in like depletion.
Absolutely, yeah, you're right. We'd get bending in the diagram. And which way would the diagram bend?
Up. So
the
the
phi
right-hand
s,
side would go up.
that's right. Yeah, the right-hand side of the diagram would go up. So imagine EO would be up here like this, right? They would be higher, but this portion here then would have to bend down like this, right? So if your EC moved up like this, EC would have to bend down like this. Your EI would be bending down like this, and then your EV would also be bending down like this. Okay, so you can already imagine that's going to impact your threshold voltage, because you're already getting some bending in your band diagram. You're already getting some inversion in your band diagram, because you see that if you take the p-type semiconductor and you bend it down like this, you're creating a potential well, or part of a potential well, for the electrons, and you're driving away the holes, right? So phi m and phi s, they matter in determining the threshold voltage. So let's go back to that diagram now. So this one is actually giving the example that we just talked about, where phi s is much greater than phi m. Okay, you can see this is the conduction band, this is the valence band, this is the intrinsic level. So what this is showing, this is a diagram at equilibrium. The Fermi level, how do you know it's at equilibrium? The Fermi levels are lined up like this. Even at equilibrium, you can see that there's band bending. A significant amount of band bending, in fact. In this example, they're showing that there's actually enough band bending to create an inversion channel without any voltage applied. What type of device would this be? Enhancement or depletion mode?
Depletion.
Yes, that's correct. Why would it be depletion?
You have the band bending without any sort of anything. You have a conductive channel without any voltage applied.
Right, exactly. Even at equilibrium, the device is on. You have a conductive channel. So that would also be referred to as a normally on MOSFET, and that would be considered a depletion mode device. In an enhancement mode device, you need to apply a voltage to it in order to turn it on. Okay, so basically we can see that however much, if there's a difference in phi ms, if you have in this case, you can see that phi m and phi s, phi m is less than phi s. So phi ms, we define phi ms as being equal to phi m minus phi s. Okay, if that's not clear from this diagram, let me make sure I put that in there. Phi ms equals phi m minus phi s. So in this case, phi ms is negative. Okay, so which makes sense, because your phi m is less than phi s, and this plays right into the threshold voltage equation. This would actually reduce your threshold voltage by an amount equal to phi m minus phi s. This phi m minus phi s would be negative, so it's going to reduce your flat band voltage. It's going to reduce your threshold voltage. So that's the first part of it. Now, what is the flat band voltage? The flat band voltage is defined as the voltage that you would apply to the MOSFET in order to get flat energy bands. Okay, so this example that we see here, this one has a bend in the band diagram at equilibrium. But if we took, how would we get rid of the bending? We would actually have to apply a positive potential to this side of the diagram. Okay, if we took this side of the diagram and applied a positive potential to it, the Fermi level would come down on the right side of the diagram. Okay, and you could see that the bending would then go away. If you brought the whole right side of this diagram down, you'd get a diagram that looks like this. How much voltage would you have to apply to eliminate the bending? It's equal to QV in this diagram, okay? And you can see the bands are flat here. That is the flat band voltage. Okay, so there's a couple things that impact the flat band voltage. The first one is phi ms, the metal and semiconductor work function, as we just mentioned. The second part of it is QI and CI. Okay, this is called interface charge. So the second effect, which contributes, is trapped charge in the gate oxide. This can be due to several possibilities, but one of them is manufacturing processes. Okay, so as one example, let's say when you're manufacturing your device, when you're growing your gate oxide layer, for example, let's say you grew the gate oxide in a furnace that had a wet ambient, but that wet ambient had like metal ions, something to that extent in it. Let's say you took your MOSFET device and ran it under city tap water when it was not in the protected state. You know, a lot of these chips nowadays, they have like protective coverings over them. But if it weren't, and you had direct access to the gate, and you put like unclean water, like tap water there, tap water has metal ions, right? So those metal ions can actually embed themselves within the material. Okay, normally we don't even know about those types of things, but when your gate oxide is only, you know, several atomic layers thick, then a single charge in the gate oxide can wreak havoc. So there's models for that. And this is what that model might look like. At the very simplistic level, okay, whenever you have positive charge, this is going to change your threshold voltage, because a positive charge is contributing electric field. Electric field is changing your potential between the metal and the semiconductor. Okay, so this is definitely going to change the potential. Another way you can think about it is that, you know, we normally apply a positive voltage to the gate metal, and then you end up getting a buildup of negative charges in the semiconductor, right? That's the process of inversion. But what if you already had some positive charges in there already that's trapped in the silicon dioxide layer? These positive charges would bring in some negative charges underneath the gate, and so this would reduce your threshold voltage. Okay, it's kind of doing some of the work for you already. Right. So these issues of like different types of trapped charges, okay, there can be mobile ionic charge, there can be oxide trapped charge, there's oxide fixed charges, and then there's some charges that can show up at the interface, what's called the interface trap charge. Some effective positive charges at the interface between the silicon and the silicon dioxide. So there's a lot of reasons why these charges can come about, but we have to take those into account. So when those charges exist, as I mentioned before, if you have positive charges in the oxide layer, that's going to create an electric field. Okay, and that electric field can actually cause the band diagram to bend. You know, depending on what the polarity of the charge is, it can the right side of the diagram can bend upwards or downwards. So this is taken into account by you know, also as part of the flat band potential, is that since these also contribute to some band bending, the phi ms also contributes to band bending. We take both of these effects into account in a single equation for the flat band voltage, the phi ms term, and then the QI over CI term. Okay, because if you have a positive interface charge, that will bring the flat band voltage down, it will also bring the threshold voltage down. Okay, a positive Q sub I, a positive interface charge, is going to bring in some of the negative charge carriers on this side, and it's already going to do some of the inversion for you without even applying a potential. That's why it would reduce the threshold voltage. It reduces the amount of work that you need to do in order to turn the device on. Questions? Okay. So this QI term, by the way, it incorporates all these different types of, it's kind of a summation of all the different types of trapped charge. And the last part here is why do we divide the QI by CI? And that is because voltage drop is equal to Q over C, just like we found on the last slide. Okay, so this term here, this is the voltage drop due to interface charge. That's why it's not just QI, it's QI over CI. All right, so let's talk about the phi MS. Now, this is something that if your semiconductor is, if your MOSFET is made out of a metal gate, and then you're using a typical semiconductor, then, well, you can just find the work function of the metal and find the work function of the semiconductor. We've already dealt with some of this stuff when we were talking about metal semiconductor junctions. Okay. Metal work function is something that would be given to you, and the semiconductor work function you could calculate based on the doping of the semiconductor. But what often happens is there's a process that's used to make MOSFETs where, again, if I draw the diagram of a typical NMOS device. So this is the gate material. So this is oxide. Let's write that out, oxide. On top of that, instead of a metal, something that's often used is N+ polysilicon. Okay. And the reason why polysilicon is used, well, I mean, it has been used in the past. There are various different types of metal, conductive layers that are used in the gate. If polysilicon is used, then you can use this chart to determine what phi MS is. The reason why polysilicon might be used is, for example, it's still conductive because it's N+, it's highly doped, so it has the conductive properties of the metal, but it's also lattice matched to the rest of the material. Okay, so that's one of the reasons why polysilicon is used as a gate metal, and it can withstand high temperature steps subsequent to to creating the gate metal. Okay, so this is substituting for a gate metal. When you have a polysilicon gate, you would just typically look up the phi MS value on a chart like this. So this is an example of an N+ polysilicon gate, P-type silicon substrate. So this is P-type substrate. So this would be for an NMOS device, and this up here would be for a PMOS device. So what you can see is that if you increase the doping, the phi MS term goes down. For an NMOS device, and for a PMOS device, it goes up. So if we just look at this, just to give you a visual, this is a P-type material, this is an N-type substrate. Okay, so the semiconductor, the metal portion of the work function is changing so that your phi MS term goes down in an NMOS device and it goes up in a PMOS device as you increase the doping. Okay, so if you have a problem like this in your homework, then or in your exam, you'll be given this chart. This chart shows some typical threshold voltage values as a function of the substrate doping and the interface charge. Okay, so what you can see here is substrate doping Na, and then the substrate doping Nd. Okay, so this is for an NMOS device, and this is for a PMOS device. So this will help you kind of see how designers would actually control threshold voltages. We can look at the metal work function as well, but that's not shown on this diagram. This diagram is mainly showing these 2 points: substrate doping and the interface charge. So what you can see is for an NMOS device, for the substrate doping, as you increase from 10 to the 13th to close to 10 to the 18th, the threshold voltage goes way up. Okay. Now, the reason for this is if we look at 2 things. Okay, it changes the semiconductor work function. Okay, the 2 phi f. If you increase the semiconductor work function, let's go back and look at that. This term. What would happen to this term if you increase the doping?
Increase.
It'll get larger. That's right. So that's one portion of it. So our threshold voltage equation, this term would certainly go up if you increased substrate doping. But it turns out this term is also important. Okay, this depletion charge term, it's the second term of the equation. You see there's a negative sign here. But if the depletion charge is negative for an NMOS device, right? In an NMOS device, we just drew this diagram here and said, like, hey, the depletion charge is negative. So if QD is negative, then you're subtracting a negative. So the second term ends up being positive for an NMOS device. And it ends up being negative for a PMOS device. Okay, so increasing the substrate doping would actually increase the depletion charge because you have a higher density of dopant ions in there. Okay, so this is also going to end up bringing up the threshold voltage. So that's why when you actually plot it out like this, you see that indeed the threshold voltage is increasing quite significantly when you go above 10 to the 15th, 10 to the 16th dopants per centimeter cubed. Okay. The second term here is the interface charge. Okay, so we finished looking at this one. Now we're looking at this one. The interface charge is shown here. This is with 0 interface charge. And then when you add interface charge to it, remember interface charge is a negative term, so it reduces the threshold voltage. So if you have some interface charge here like this at 10 to the 11th, then it goes down by this much. If you get down to 5 times 10 to the 11th and 10 to the 12th, you can have a significant reduction in your threshold voltages. Okay, so this kind of brings up the importance of having clean and reproducible manufacturing processes. Let's say you have a big wafer, and in one side of the wafer, you have some process that dumped some interface charge on one side, but it didn't do the same on the other side of the wafer. Your transistors on one side of the wafer would have a different threshold voltage than the other side, and that would become a manufacturing reliability nightmare. Okay, so that's one of the reasons why we didn't just go to 12-inch wafers right away. Back in the 60s and 70s, there were like 4 or 5-inch wafers. They improved the manufacturing processes to make it very reproducible over that area. And then as the reproducibility improved, we're able to go to larger and larger wafer sizes. Okay, so in general, interface charge would decrease the flat band voltage, and so it decreases the threshold voltage as well. And then this is showing the same for a PMOS device. So some of the polarities are flipped for a PMOS device. Remember, for a PMOS device, the threshold voltages are negative, right? So you have to apply a negative VGS in order to turn the device on. So that's why these are all negative. But the relationships here also hold true. When you add interface charge, the threshold voltage for a PMOS device gets lower, so it becomes more negative. And as you increase the substrate doping, the magnitude of the threshold voltage gets larger. Okay, because of that depletion charge term that we saw in the equation. That depletion charge term is negative for a PMOS device, so that makes this more negative as you go to larger substrate dopings. Okay, so these kinds of graphs are important because if you want a certain type of device, you'll have to bias, or you'll have to dope the substrate in a certain way. And you also have to consider surface charges too. If your process gives you a surface charge of, let's say, 10 to the 11th, okay, and you want to have an enhancement mode device, what is the minimum substrate doping you need to have an enhancement mode device?
Somewhere between 10 to the 15th and 10 to the 16th, somewhere around there, to get a positive threshold voltage.
Exactly, right. So for an enhancement mode device, you want your threshold voltage to be positive. So you're at 10 to the 11th here, so you're along this dotted line. You see at what doping level does the threshold voltage become positive? Right about here. So using graphs like this, designers could decide what the process should be. Okay. And if they measure a certain threshold voltage, well, then they can use that to sort of back out what the interface charge may be. If you already know the substrate doping, for example, you could use a chart like this to figure out the interface charge. Okay, so let's now get to an example. Okay, in this example, we're going to do this one together. We are going to calculate the threshold voltage for a MOS transistor on P-type silicon with substrate doping 5 times 10 to the 15th. Okay, and with these parameters. This has a polysilicon gate, so I just want to make sure everyone's aware of that. This example, you have a polysilicon gate, and you have a substrate doping 5 times 10 to the 15th. You're given that the thickness of the oxide layer is 100 angstroms, and the interface charge is 4 times 10 to the 10 times Q. Remember, Q is 1.6 times 10 to the negative 19 coulombs per centimeter squared. So we're going to go over this as a class, but I would like everyone to try this on your own for a few minutes, because I want you to see like where you get stuck. So again, I would like everyone to just go ahead and try this for 5 or 7 minutes. I'm gonna mute myself and just see how far you get. Okay, you can use the notes that you have from the lecture, and I'm just gonna pause the recording for a little bit here. I'm gonna mute myself, and then we'll come back in 5 to 7 minutes and do this problem together. If you have any questions during that time, just put a message out in the chat. Okay, so I just went ahead and started the recording again. I'm going to switch back to a pen. We're just going to go through this step by step. And again, the goal is to save yourself some time on the homeworks. I'll show you how to go through these problems and just address some of the the key little parts of it that are often like gotchas. Okay, So we'll start by drawing the device. So the device will look something like this. Imagine a typical NMOS device. So you have an N plus source, another N plus drain. Then you have the gate oxide here. Okay, this is an oxide. This is SiO2. And this has a relative dielectric constant of 3.8. So the gate here, the gate is polysilicon. And this is going to be an N plus polysilicon. So we're going to look up that. We're going to look up that in a chart to find out what phi ms is. Then we have the p-type substrate. And this has a doping of Na equals 5 times 10 to the 15th per centimeter cubed. Also, the oxide has a thickness, I forgot to mention that. Tox is 100. That's angstroms. So it's going to be 10 to the negative 8 centimeters. Okay, 1 angstrom is 10 to the negative 10 meters. So it's 10 to the negative 8 centimeters. And the interface charge, I'm just going to put a little arrow here to show that the interface charges are in the oxide region. And those interface charges have a density of 4 times 10 to the 10 times Q, which is 1.6 times 10 to the negative 19 coulombs per centimeter squared. Okay, so that's the information that we have. And we are asked to find the threshold voltage. So let's write down the threshold voltage equation. The threshold voltage equation is the flat band voltage, VFB, minus QD over CI plus 2 phi F. Okay, and we're just going to do these in different parts. So this is going to be, we'll say this is part 1. We'll do this one first, and then we'll do this one second, and we'll do this one third. Okay. The order kind of matters because the 2 phi F calculation, it's easier if you do this one first before doing the second one. You'll see what I mean. Okay, so step 1, we're going to find 2 phi F. So this is the surface potential. So phi F equals KT over Q, ln of Na over Ni. Okay, and this is going to be 0.026 ln of, so you put your substrate doping in here, 5 times 10 to the 15th over 1.5 times 10 to the 10. Okay, so let's just go over the key things here. Remember, KT over Q at room temperature is 0.026 volts. And then you have this log term here, substrate doping over Ni. Ni is 1.5 times 10 to the 10 at room temperature for silicon. So you end up getting 0.29 volts here. Okay, so the 2 phi F term is going to be 0.58 volts, 2 times that. Okay. All right, so this is a portion of your threshold voltage. So this term here is coming out to 0.58 volts. So how does this term depend on what are the dependencies of this term? Well, you have a substrate doping term here. Substrate doping, and there's a logarithmic dependence on the substrate doping. Okay, now, next portion here is the depletion charge term. We're going to figure out QD over CI. This is the one that requires the most calculation. So let's figure out the CI first. Okay, now this CI term has to do with the oxide capacitance. Okay, so the unit capacitance is the epsilon of the oxide divided by the thickness of the oxide. Okay. So this is going to be epsilon R times epsilon 0. So we put in our relative first. The relative dielectric constant is 3.8. And then the epsilon 0 is 8.85 times 10 to the negative 14 farads per centimeter. And the thickness of the oxide is 100 times 10 to the negative 8 centimeters. So this comes out to, let's see, 3.36 times 10 to the negative 7 farads per centimeter squared. All right, so there's our unit capacitance. The next thing we have to figure out is the width of the depletion region. In order to figure out the depletion charge QD, we first have to figure out the dimensions of the depletion region. So just as a note, just to remind everyone what we're calculating, this diagram, this we're trying to find QD, and I'm saying in order to find QD, you need to first find the width of the depletion region. So this is what we're calculating first. We're calculating the depletion width, WD, and then from there, we can then calculate the depletion charge as Q times NA times WD. All right, so let's go back to our example. Oh, okay. That's actually what I had done the previous term. That's fine. I think we'll just go through this step by step so you can see it. So the depletion width is 2 times the square root of epsilon of silicon phi f over Q times N of the substrate. Okay, so the thing I want to make sure that you understand is this is for silicon. It's not for oxide. Okay, so for this term, we have to do 11 times 8.85. So our relative dielectric constant is 11, not 3.8. Okay, and then the reason we did the phi f calculation first is because you use this here. So we calculated phi f as 0.29 volts. So that's where our 0.29 is going to come in there. Divided by 1.6 times 10 to the negative 19 times 5 times 10 to the 15th. That's our substrate doping. Okay, and when you do this calculation, it comes out to 3.76 times 10 to the negative 5 centimeters. Okay, so sanity checks, 10 to the negative 4 centimeters is a micron. So this is coming out to like 0.37 microns. So, you know, your depletion widths should be on the order of submicrons to maybe tens of microns. In a MOSFET, is typically smaller. So I think this is a reasonable number. And so the QD then is negative Q times NA times WD. And our NA is 5 times 10 to the 15th. Our WD is what we calculated up here. Q is 1.6 times 10 to the negative 19. And so this comes out to negative 3.1 times 10 to the negative 8 coulombs per centimeter squared. Remember, this term is negative, right? For an NMOS device, your QD should be negative, and for a PMOS device, it should be positive. And the final part here is calculating QD over CI. Right, that's the second term in the equation. So QD over CI is negative 3.1 times 10 to the negative 8 divided by 3.36 times 10 to the negative 7. Units up here is coulombs per centimeter squared, and the units down here is farads per centimeter squared. Okay, and the units that you end up getting is coulombs per farad, which turns out to be a volt. So it's negative 0.092 volts. All right, so that's the most involved portion of the calculation. And the third part here is the flat band voltage. Flat band voltage is equal to phi ms minus Qi over Ci. In this case, we found phi ms from the chart. Okay, if we go back to this chart here, all right, this is an NMOS device. We look in the NMOS device, the doping density here is 5 times 10 to the 15th. So this is 10 to the 15th, 5 times 10 to the 15th. This is about 2, this is about 4, it's about 6. So just putting it right about here. Okay. So this is about negative 0.9 is our 5 ms. So negative 0.9 volts from the chart. And then finally, we have to figure out Qi over Ci. So the Qi we're given 4 times 10 to the 10 to the 10. Times 1.6, 10 to the negative 19 over 3.36 times 10 to the negative 7. The units up here is coulombs per centimeter squared, and the units here is farads per centimeter squared. Again, when you divide coulombs by farads, you end up getting volts. This comes out to 0.019 volts. And then the flat band voltage is phi ms minus Qi over Ci, negative 0.9 volts minus 0.019. And this comes out to negative 0.92 volts. Okay, so you can see in this case, most of the flat band voltage came from the phi ms term. And very little of it came from the Qi over Ci, the interface charge term. So in this case, you could say that the interface charge was relatively insignificant. All right, so now overall, we have to put the whole thing together. So I'm just going to put this in a box here since we have some space here. The VT equals the flat band voltage minus QD over Ci plus 2 phi f. So negative 0.92. Then the QD over Ci is negative 0.092. This is a negative term and you're subtracting a negative term, so this is going to end up being positive. And then your 2 phi f term is 0.58. Okay, and this comes out to, whoops, negative 0.25 volts. Okay, so you can see in this case, the flat band voltage contributed most to it. QD over CI contributed very little. The depletion charge contributed very little, and then the phi F term was significant as well. So the first and third terms are the most significant ones. And this ends up being negative 0.25 volts as a threshold voltage. So what does that mean? Is this an enhancement or depletion mode device? So you have an NMOS device with a negative threshold voltage.
Depletion.
It's going to be a depletion mode device. That's right. Good. All right. So that is calculating threshold voltages for an NMOS device. Okay, you're going to have a problem like this in your homework. So let's end with this today. Methods of controlling the threshold voltage. So just like we did with the diodes, remember we said, like, we drew that chart with the diodes and we said, well, these are the performance parameters for a diode would be things like the breakdown voltage. It would be the built-in electric field. It's the built-in potential. Like, all those things are performance parameters for a diode device. And then we looked at, well, what are the things that we can control about a diode? We can control the doping. We can control the material that we use, the band gap, and we can also control the area of the diode. Those are the three things that are within our control. With the MOSFET, there's actually a lot of different things we can control. So we can control the substrate doping, we can control which type of metal we use, we can control the gate oxide thickness, junction depths. That's something we haven't really talked much about. Different materials can be used that create, different energy band diagrams. There's a lot of different things that go into the design of a MOSFET. In your careers, you're probably going to see a lot of change in those types of things. We already have over the last 4 decades, and I expect that would probably continue. So let's just talk a little bit about the methods for controlling the threshold voltage, and we'll end there today. So let's starting with phi ms. We found in our example problem, we found that phi ms is, in the case of this polysilicon gate, it can be adjusted by how much doping you do. Okay, so one of the reasons polysilicon is used instead of metal is due to the high melting temperature. With metals, you can choose your metal work function very specifically. With polysilicon, it's dependent on the doping. So you have a little bit less control there, but this is a manufacturing issue that we really haven't talked about very much. After, after laying down some of the gate material, there's some high temperature processes that may need to be done afterwards. And if you use a metal there, then you can't do any high temperature processes after that because the metal will melt. Okay, so phi F, as we found out, this depends basically on the substrate doping. So it's a logarithmic function of the substrate doping. The Q sub I depends on oxidation conditions. So this is the interface charge. When you're growing the gate oxides, you start off with this silicon substrate, and then you grow this thin oxide layer on top of it. That has to be done in a very, very controlled way. Okay, it's a very thin layer of oxide. The quality of that growth has to be done very, very carefully. It's typically done by putting a silicon wafer in a furnace for some period of time. And the temperature in the furnace, and the time in the furnace is very well controlled. One of the reasons why silicon is such a popular material for MOSFET devices is because you can actually grow a high quality oxide on top of silicon, basically by putting it in a furnace. So you kind of get this material for free. All right, so QI depends on oxidation conditions. Those have to be controlled. CI also depends on oxidation conditions because the oxidation conditions will determine the thickness of the gate oxide, the oxide thickness, and the type of material that you use will determine your epsilon. So you the unit capacitance CI is equal to epsilon oxide over the thickness of the oxide. So a typical gate oxide thickness, as shown in this diagram, might be 0.01 microns, or about 10 nanometers. Okay, now they've gotten even thinner than that. So if you use silicon dioxide, your epsilon of the oxide is going to be 3.8. Intel and other companies have moved to high K dielectrics, and the reason for that is they want to have a more control over the threshold voltage. Okay, and just as a physical concept, one thing to remember is that the capacitance is epsilon oxide over the thickness of the oxide, right? So the higher the dielectric constant is of this oxide layer, the better a capacitor it is. The better the capacitor it is, the more control you're going to have from the gate into the channel region. Okay, so you'll also have control over your depletion charge. So that's the reason why some companies went to high dielectric constant materials that might have dielectric constants of 5 or 10 or maybe even more. Some of the key issues with this, okay? A lot of times we want to increase the oxide capacitance because this would reduce the threshold voltage needed to turn on the device. Otherwise, you'd need large threshold voltages, and that consumes more power. Okay, so we want to increase the CI. Increasing CI would allow us to have better control over the channel, okay, without applying high voltages. But so you could reduce the thickness of the oxide. If you reduce the thickness of the oxide, that'll of course increase the capacitance. But this will also result in something called gate leakage currents. You can get tunneling currents. We'll talk about that later. So the other option is to just increase your dielectric constant, and that's why companies use high K dielectrics. Examples would be oxynitrides. The last point here is another way of controlling VT, which is actually very important and is done in industry, is a method called ion implantation. So here what happens is that you deposit a precise amount of the impurity just underneath the gate. And it turns out this can modulate the threshold voltage. So let's look at this for an example. This is a PMOS device. I know we haven't spent too much time looking at PMOS devices, but remember that the source and the drain are P-type, substrates N-type, and the channel, the conductive channel that connects the source and drain regions, those are also going to be P-type. Okay, so if you start out with an N-type material and you want to make a P-type, of course, you can apply voltages to the gate, like we've talked about. By placing a voltage on the gate, you can drive away the majority electrons and pull in the, let me just draw this out. By applying a voltage to the gate, you can drive out the electrons and pull in the minority holes to create a conductive channel. But one thing you can do to modulate the threshold voltages is that you can dope this with boron. Okay, if you dope it with boron, you already end up having some boron. The boron atom is it's a column 3 dopant. So when the column 3 dopant goes away, it leaves behind a positively charged. And when the hole leaves, it leaves behind a negatively charged depletion region. So this would end up having an associated negative charge. Okay, you're creating a negatively charged doping there. Okay, so you've created you've doped the material, and by doping the material, you can modulate the threshold voltage. And with this ion implantation, you can control the depth and impurity to very precise levels. Okay, so these implants are done in a furnace, and they can be used to control the threshold voltage throughout the entire device. Okay, we'll pick up here. I know we kind of rushed through this a little bit at the end. We'll pick up here, and next time in class, we'll talk about the second order effects in MOSFET devices. We'll talk briefly about the horizontal energy band diagram, and then get into some of the second order effects like leakage currents, short channel modulation effects, and then the body effect. Okay, we'll hopefully, we're going to do the presentations on Wednesday, so we'll start talking about this. And if we finish it on Wednesday, then Monday we'll just review. Otherwise, we'll spend a little bit of time Monday going over second order effects. Okay, so let's end here for today. Any questions before we end today? Okay, great. I'm going to end the recording then for today.